Okay, I think we can start working on the last case now. A1 cap changed into A1 changed into 0. What is it? 3, 6. Okay. Again, this is basic, and when you compute Y1 cap, you get 3 and 9. And since y11 is not equal to 0, obviously we have a basis. B cap consisting of x1's column and x5's column, 3, 6, and 1, 0, or 0, 1. Which one is that? x5 is 0, 1, yeah. This is a basis. We know that for sure. And so we enter that. In other words, we revise the tableau. Three 9 goes into here. I need also R1, which is CB B inverse A1 cap minus C1. CB is minus 2, 0. B1, B inverse, please close the door. B inverse A1 cap is 3, 9 minus C1 minus 2. How much is this? Minus 6. So that's going to be minus 2. Minus 2 times 3 is minus 6, plus 2 is minus 4, sorry. Minus 4, yes. Mm-hmm. Thank you. And the right-hand side value is still minus 12 here. Okay. Now, you need a unit vector here because we work with B inverse rather than B. For that reason, you need to transform this into the unit vector that has a 1 in the circled element, zeros elsewhere. So you pivot on that. To transform the tableau into a new one. Just on the right time. They went into the classroom. Okay. All right. Let me just copy from my notes. At the end of pivoting, we get 1, 0, 0, 0, 1, 0. Minus 5/3 here, 1/3, and 0, 1/3, 1/3, minus 2, minus 2/3, 1/3, minus 2, 0, 0, 1, and minus 4 here, 2 and minus 8. That's what I've got, if I did not make a mistake. All right, so at this point, we see that primal feasibility is lost because you have a minus 8 here. We also have dual feasibility lost because we've got a plus entry in X3 column. Okay? So we've got the most complicated situation as far as sensitivity is concerned. And so what I'm going to do is multiply the row. Thank you for reminding me. Yes, I must have written it down, right? Multiply this row by minus 1. And that's going to give me a plus entry here, minus here, plus, plus, like that. So we changed everything. And then I need a unit vector. So I introduce artificial variable x6 here, which gives me 0, 0, 1. So that's the way constraints look now. Okay? Of course, we're going to use phase 1 now. So you just scratch the top row out. You should be doing this sequence in a sequence, but on the board it's easy to erase. So you've got zeros here, by the way. In phase 1, of course, this is going to be minus 1. This will change it into 0. Okay? You're minimizing x6. And then you add plus 1 times that, so that's 0. This becomes what? Minus 1. That becomes 2. This becomes 2. 0, 0. Okay, the other ones don't change. All right, so now we have the phase 1 initiating tableau. And then we enter, for example, that one. And then we look at the ratios, which one is smaller here. That's 6, this one is 4, so this one goes out. Right? You pivot on that, etc. You know how to carry on after that. Okay? The fourth change, add x6. All right, when you add a new activity, the easiest viewpoint to handle this situation is to simply imagine or pretend that it had been in the problem all along from the very beginning of the problem, except that you always kept it as 0. x6 is always 0, or you just pretend that that was the case. So it's been kept as a non-basic variable. Now all you have to do is, well, maybe I should enter it. That's the question you ask yourself. So all you have to do is enter that particular column into your optimum tableau and see if you should enter or not. Okay? So to do that, you compute R6, which is CB B inverse A6 minus C6. How much is CB B inverse? It's minus 2, 0. And A6 is minus 1, 2, minus C6, 1. How much is this? 2 minus 1. So that's 1. So you will enter that. Okay? And to do that, you need to also compute Y6. That gives me minus 1. This gives me plus 1. The rest of the tableau is the same old tableau, so I'm not going to write them down. You're entering this guy, and this one should exit, and you just pivot and see what you get. Number 5. Add new constraint. What was the constraint? Minus x1 plus 2x3 is greater than or equal to 2. Again, in general, the way you should look at this is you've got some kind of a feasible set with the old data. Suppose that's your feasible set. And suppose that's your optimum, say x bar optimum solution here. Now, when you have a new constraint, one of two things can happen. One thing that can happen is this is the new constraint, and it chops off a portion of the old feasible set. This part is chopped off now. But the optimum point is not chopped off. Now, x bar was the best of all available points in the original feasible set, which included also the shaded part. Since it was better before, now that some points are chopped off, it will certainly be better also in the new situation. Okay? So, in this case, if x bar is feasible relative to the new constraint, it is still optimal. That's the obvious conclusion you've got here. Okay? The other possibility is, of course, the case when you have optimum being chopped off by the new constraint. This is the new constraint, and certain part of the feasible set is cut off, and it includes also x bar. In this case, of course, x bar is no longer feasible, and so it's no longer optimal. You need to compute the new optimum solution and use dual simplex method because you lost primal feasibility. Okay? So, back to the example. The old optimum solution is x1, x2, x3, x4, x5. x1 is how much? 6. x5 is 10. The other ones are all 0. Okay? That's the old optimum solution. Check to see if the old optimum constraint, if the old optimum solution satisfies the new constraint. The constraint is minus x1 plus 2x3 greater than or equal to 2. While x1 is 6 plus 2 times x3 is 0. And is this greater than or equal to 2? The answer is no. It's not greater than or equal to 0 because minus 6. Okay. So we are into the second situation. Okay? So we need to compute the new solution now. Okay, so that's the old tableau. The new constraint has a coefficient of 0 for this one. x1 has a coefficient of minus 1. x2 has 0. x3 has 2. 0, 0. Of course, I need a surplus variable x6, which is going to have a 0 cost here, 0, 0, 1. That's the situation. And we have 2. You made everything into the standard form now. Sorry, that's minus 1. Yeah, that's minus 1. That's a surplus variable. Now, you don't have a basic variable here because you need a basic column, or you need a unit vector. x6 does not do the job. You may wish to insert x7 as an artificial variable and continue like that. But before doing that, you may also decide to use x6 by multiplying everything through by minus 1 in the last row. Okay? So when you do that, of course, things change. That becomes plus 1, that becomes minus 2, this becomes plus 1, this becomes minus 2. Now I can use this. Or can I? Yes, it looks like I can use it. There's only one problem with this tableau. What is that problem? x1 is supposed to have a unit vector, but it doesn't. See, you need to revise these things. Also, x5 must also have a unit vector. Well, it does, unfortunately. So you need to get rid of this 1 here. And to do that, what do? You add minus 1 times that, which changes this one into 0, this one into minus 1. That is minus 3 now. This one is minus 1, 0, 0, 6, minus 8. Changes into minus 8. Lots of stuff to take care of. And then, of course, you realize that you've got this handy method, the dual simplex method, to use because you've got a negative here. And then you use your regular ratio test. Which one goes out here? Minus 3 to minus 1, minus 1 to minus 3, minus 2 to minus 1. Which one is the smallest in absolute value? This one, right. So you pivot on -3, and that should get you to a new tableau, which has that particular infeasibility removed. Okay? It may or may not turn out to be an optimum tableau. It depends on the top row, the row 0 numbers. Okay. That's it for sensitivity analysis. So we'll talk about some parametric analysis now. You followed it so well, I have to continue with this. Or maybe I shouldn't. In other words, I may also switch to decomposition, actually. In which case, of course, you will have to read the material on parametric analysis on your own. Which one do you want to do? No answer. He's a diplomat, I guess. Yes, he knows how to say it. Yeah. Okay, let's talk about the parametric analysis. Maybe not too much in detail, but at least to some extent. By the way, there's also the so-called range analysis. Maybe I should mention that very briefly. In that case, you may be asking for a given parameter, what is the range of values for that parameter such that the old optimum continues to stay optimal? Okay? So, allow only one parameter to vary, and then ask yourself the following: with all other parameters fixed at their old values, what is the range of values for that parameter for which the old optimum is still optimal? That's the question you're trying to answer. Of course, the isolated parameter could be a Cj value, could be a Bi value, could sometimes also be an Aij value. Other than that, we don't have. So this is a very special case. It's a little bit more general than sensitivity analysis because you allow the parameter to not assume a particular new value, but rather you're asking yourself, what are the collection or the family of new values for which the old optimum is still optimum. I'm not going to go into this, but for example, if you were, for example, asking yourself if range for C1, what is the range for C1, for example, in the old example. Is C1 a basic variable or not? It is a basic variable. So in the old example, all you have to do is you compute R, which is CB, B inverse A minus C. Except that this particular parameter is now taken to be C1, an unknown number. Okay? It's a parameter. What is the second C1? C5. C5 was 0, right? And then B inverse A was whatever it was. What was it? Someone, I erased the whole stuff. 1, 1?
0.
1, 0? 0, 1.
That's right.
0, 1? Second column. Oh, 1, 1, 0, 1, third column. No, CB is this one. B inverse A is 1, 0, 1, 3, 1, 1, 1, 1, 0, 1. That's my B inverse A. Bless you. Minus C. C has C1 here. Then 1, minus 1, 0, 0. These are the components. Okay? And when you multiply them out, you get C1, 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 0 minus this guy, which gives you, what does it give you? C1 minus C1 is 0, C1 minus 1, C1 plus 1, C1 minus 0, so it's C1, and then 0. So you get this reduced cost vector. And then for optimality, you want this to be less than or equal to 0 in each component. Okay? So that tells you C1 must be less than or equal to 1. C1 must also be less than or equal to minus 1. C1 must be less than or equal to 0. That's it. So you've got these numbers. Of course, the minimum one will be the effective one. So the range of values for C1 in order for that will keep the old optimum optimal is this. Okay, that's the range. It's simple stuff, so I'm not going to go into further detail on this. For range analysis on BI, you have to look at the feasibility, primal feasibility conditions, and you can do that. If you have an AIJ, I will leave that up to you to figure that out. Okay? That will affect both reduced costs as well as primal feasibility conditions, possibly. So you have to take care of both. Okay? All right, now parametric analysis. We're going to look at only two cases of parametrization, either parametric costs or parametric right-hand sides. So let me go with the first case, parametric costs. Suppose we have a minimization problem. The cost function is parameterized. So rather than having a constant or fixed vector c, you have a fixed vector c plus another fixed vector c prime times a lambda. Lambda is just a parameter, okay? Times x. Subject to ax equals b, x greater than or equal to 0, where c, c prime are n by 1 by n vectors, given vectors, okay? And lambda is a parameter, and it's assumed to be non-negative. Could be also negative. It doesn't really matter, but let's just keep it simple and assume it's non-negative. So the question is, well, assuming when lambda equals 0, this has a fixed cost, c. Suppose you solve that problem, but then you allow lambda to start varying from 0 up. How does the optimum get affected? And how do I compute the new optimum? And if I allow lambda to vary all the way between 0 and plus infinity, how things will change. That's the question, okay? All right, the way to do this is really not too difficult. Assuming that your feasible set admits an optimum solution, at least at lambda equals 0, okay? So let's not worry about the unbounded case, etc. So I'm just going to assume the problem is not unbounded. So if we call the problem given here P of lambda for fixed lambda, assume P of lambda is not unbounded. Okay, let's just make that assumption. Now what I'm going to do is, if I ask this question, how does the optimum change as a function of lambda? Usually when I ask it on an exam, I typically get an answer from students which is based on simplex tableau, basis, etc., which is a rather bad way of actually envisioning what's going on. Okay, it's not a good way. So rather than doing that, just look at this geometrically first. Okay, then we'll switch it into the algebraic form, the simplex tableau. All right, when you look at this, the first thing you should do is probably, well, at least the first thing I do is the following. I just define a variable here, say z of lambda, which is the optimum objective value of the problem associated for fixed lambda. So P of lambda is this problem, and z of lambda is the optimum value of that particular problem. It is not the following. It is not this. Okay? It is not that. Because a lot of you are tempted to think about that. But this is 30 years of experience, I know that. When I define z of lambda in this particular way, a lot of people think that this is the same thing as having the objective value given by some x here. Yes, if x is the optimum x, it will be okay, but if it is not optimum, no. So, I don't want to have any confusion about what we're talking about here. It is the optimum objective value of the problem P of lambda, assuming that P of lambda has an optimum solution. Okay? All right. So here's a claim. Without doing any further analysis, you can immediately conclude that z of lambda is actually a piecewise linear function, which is also concave. So as a function, not for fixed lambda, but z as a function of lambda is a piecewise linear concave function. Does anybody see why that's the case? That's the typical question I ask in an exam if I don't cover that, and typically I don't I sometimes get the answer from few people, but most of the students, they get to think about this in terms of the simplex tableau and basic solutions and so forth, which is really, as I said, not a very good way of looking at it. Okay, so anybody seeing the solution or the why this is true, just from geometrical considerations? One minute for you to think about. Yeah. This is the lambda axis, non-negative. This is z of lambda. Claim is it looks something like this. Okay. Last piece extending all the way to the plus infinity. Piecewise, sorry, this is convex. I need to make it concave. It's the concave version, yeah. Something like this. Whatever. Okay? Okay, 1 minute is up, I think. So, let's see why this is the case. It's really very simple. But, somehow you must have that particular angle to look at the problem. So, let, say, x1 up to x, whatever, t, be the extreme points of the feasible set defined by ax equals b and x greater than or equal to 0. Okay? The feasible set is, has nothing to do with lambda. So this is a, say, let's just call it, say, capital X. This is the feasible set. And it's got extreme points because it's a standard form problem. And the optimum, by assumption, exists. So there will be an extreme point optimum solution. So z of lambda, for a given lambda, for every lambda greater than or equal to 0, z of lambda is going to be the minimum of c plus c prime lambda x I between 1 and t. So even though there are many, many, many extreme points in general, one of them will give you an optimum solution. Okay? So if you evaluate the cost vector for fixed lambda at every optimum point, at every extreme point, you get this value. This is the value, objective value for the ith extreme point. So for fixed lambda, you simply imagine yourself evaluating the objective value at every extreme point and then picking the smallest of them, because we're minimizing. So when you look at this, you're simply minimizing cxi plus c prime times xi multiplied by lambda. This is just a constant. Call it alpha I. It's the dot product of Cn, ith extreme point. This is also another constant. Call it, say, beta I. Okay? So this is simply, so this whole thing is alpha I plus beta I times lambda, which is just a linear function with intercept alpha I, slope beta I. That's it. These are numbers. Alpha I and beta I are numbers. There are no vectors any longer. Okay? So this is the minimum of all these linear functions. Even though there are many of them, when you look at linear functions with different kinds of slopes, whatever they are, you know, for each fixed for each fixed lambda, for a given lambda, you're looking at the minimum of them. So you're taking the pointwise minimum of these functions. And the pointwise minimum, this is not a good picture. Let me just erase that one. I made it incorrect, yeah. That's convex. Anyway, yeah. The initial picture was correct, yeah. I don't know why I changed it. All right, so when you look at the pointwise minimum, it's going to pick up the smallest of these linear pieces, and then we'll switch to another linear piece. And then we'll switch to another linear piece, so on and so forth. Okay, so the global characterization of z of lambda is this function defined by the cross-hatchet portion of these curves, and it's piecewise linear. So the initial picture I draw was right. Why did I switch that? I have no idea. It was like this, right? Okay. Please, yeah, let's correct that also. All right, so this is the situation. Now, how do I compute this piecewise linear curve without having to enumerate all of these extreme points? See, that's another question. Knowing something is piecewise linear is fine, but knowing how to construct it is something else, okay? So, how to construct Z? That's the next question. Well, it's quite simple. Solve P of lambda at lambda equals 0, which means you solve the problem, minimize Cx, Xn, the feasible set. Lambda is 0, okay? Suppose optimal basis is, say, B, and it defines your optimal solution, okay? So this tells you that you have the starting point in the picture. You've got the starting point here. But then this piece, you have to figure that one out, okay? What is the piece? So in this case, if you look at the reduced cost as a function of lambda, this is not a multiplication. It's the reduced cost vector as a function of lambda. How much will it be? It's the optimal W vector, which is CB B inverse. Let's just write it that way. CB B, well, CB is also a function of lambda. CB is what? CB plus CB prime times lambda. That's your CB, as lambda is varying. Times B inverse, which is not dependent on lambda, times A minus C, which is C plus C prime lambda. Okay? That's your reduced cost. And what do you want? This is by definition. That's your reduced cost vector. You want this to stay less than or equal to 0 for a certain variation of lambda from 0 up to whatever value it can get to. Okay? So let lambda be the value of lambda such that R of lambda stays less than or equal to 0. Okay, the first switch point. How do I compute that? Well, it's really simple. You just compute this stuff. CB, B inverse A minus C. This is the reduced cost vector at lambda equals 0 plus then CB prime B inverse A minus C prime times lambda. That's the lambda dependent portion of the reduced cost. And you want that to be less than or equal to 0. So these are already available. That's your RJ, if you look at this one component at a time. This part is also computable. Let's call it, say, RJ prime. So for every j going from 1 to n, Rj coming from here plus Rj prime lambda is supposed to be less than or equal to 0. Okay? Now, if Rj prime is negative, lambda being non-negative, Rj is also less than or equal to 0. We know that for sure. How do I know that? Rj is the value you have at lambda equals 0. Okay, so that's less than or equal to 0. If Rj prime is also less than or equal to 0, of course, this will always continue to stay as less than or equal to 0. Okay? However, if Rj prime is positive, then this is increasing gradually as lambda increasing. So it may turn positive. So lambda 1, this first switch point is infinity if Rj prime is less than or equal to 0 for every j. Otherwise, lambda 1 is the smallest of minus Rj divided by Rj prime. Over those j for which Rj prime is positive. Right. Whenever Rj prime is positive, this is going up. Okay? So you begin here and you continue for a while until lambda 1 with the same basis. So the initial basis B is active here. What is the slope of this? Yes? Alpha 1, which is what? CB, B inverse, etc. You know, whatever the definition I used for alpha I, what was it? CB, B inverse? Louder, please.
Alpha 1 was the intercept.
Yes, that's what I'm asking. Okay. Yeah, okay, fine. This is alpha 1 here, beta 1. Okay. Tell me the slope. I wrote it down, please. Come on, Sibel. Yes. I mean, I erased it. I don't want to derive it again. Are you guys following me? It's unbelievable. All right. This was the situation. I have to do it on my own. You are looking at the ith extreme point, right? And this gives you Cxi plus C prime xi times lambda. And my alpha I is this one. my beta I is this one. That's what I was asking. So if your first extreme point is your first basic feasible solution, that's your alpha 1. And this is your beta 1, defined by this point. So that's going to be, the slope will be C prime times, or CB prime times, XB solution, which is CB prime times B inverse B, where B is the initial basis that you obtain at 0. Okay? So beta 1 is that. That's your slope. And a little bit increase when you add a little bit, a small positive epsilon to lambda 1, of course, things will become different. You will have a different slope. So you have to figure out which new basis is valid here. And you can do that by increasing your lambda 1 a little bit, which will make your R of the reduced costs, one of them will turn positive, at least one. Which one? Whichever one gives you a minimum ratio, it will turn positive. Okay? So if you have a single one that turns positive with a small epsilon, then you have the slope, or the new basis. Okay? If you've got more than one minimizing ratio here, you've got a bunch of qualifying ones. And so in that case, you may have many different linear functions here. The one with the smallest slope will be the effective one, because you're looking at the pointwise minimum. In that case, you choose the, out of the tied ones, you choose the one that gives you the minimum slope. I'll stop here. Okay.